This question is different than what we have seen before with thermal math. Because it's asking us to find the heat capacity of a metal. Just like a lab that we're about to do. So there's no longer multiple steps involved. What it says you're going to do, and you will be doing the same thing, is you're going to get water boiling. And you're going to put metal in that boiling water. What temperature does water boil at? It's 100 degrees Celsius, right? Boiling point is 100 degrees Celsius. So we're going to put metal in boiling water for a fair amount of time. What temperature would the metal become if it sat in boiling water long enough? 100 degrees Celsius, right? Then what we're going to do is we're going to take that hot metal and we're going to transfer it into a calorimeter with room temperature water. Now, the term calorimeter was actually introduced to you last semester when we did the whole water and ice thing, but our styrofoam cups are a calorimeter. It's just a container that we can do experiments with dealing with thermal exchange. So basically, those metal rings that were at your lab bench, they get heated up, they get put in water, and then with a few measurements, notice the measurements that are on the board, we can figure out what I underlined in red to find the heat capacity of the metal. In order to do this, we are going to need to figure out two things, and that's what makes this a little bit tricky. So, we're going to first solve for how much heat, remember that's the letter Q, will water gain when you put something hot in? Remember the question says we're going to take metal, we're going to get it really hot, we're going to put it into our styrofoam cup calorimeter. The water inside of there is going to heat up. So we need to figure out how much heat will it gain. To do that, we use Q equals MC delta T. The mass of the water is given to us, 123 grams. The C value for liquid water is given to you on the top of this sheet of paper. 4.184. That's our joules per gram degree Celsius. And then notice we're given the initial temperature of the water and the final temperature of the water. We can solve for delta T, final minus initial, 13.4. By multiplying this out, we can solve for how much energy did the water gain when you put something hot in it. If I ignore sig digs on this step, I believe it gives me 6,896 joules. Really, I should be doing 3 sig digs, but then I'd have to round this up, and then that would round up here. So to write 6,900 with 3 sig digs, I'd have to start doing scientific notation. It's kind of tricky, so let's just keep an extra digit for now. Okay. We're halfway done with that problem, but I want to make sure, again, we understand what we're doing. If we take metal that's really hot and put it in room temperature water, that room temperature water will gain heat. We just solve for how much heat that water would gain. If the water gains 6,896 joules of energy, how much energy did the metal lose? 6,896. Remember, conservation of energy law. If something gains, something loses the exact same amount. So what I do with a problem like this then, and I'll do this in a different color just to separate it, I'm going to set up another Q equals MC delta T, but do this for the metal. And for starters, I know my Q value, negative 6,896 joules. Again, the conservation of energy says if water gained heat, the metal lost heat. So that's why I put a negative sign in front of it. You know, something that popped up on the homework, popped up a little bit on the activity you were doing here as well. The positive values indicate endothermic, something gained energy. Negative values indicate something lost energy, exothermic. The mass of the metal is given to me in the top as well, so I can plug in for my M, 75G. The C value is what we're solving for, the heat capacity. Again, your lab today titled Heat Capacity of a Metal. We want to solve for that value. So that's going to be my variable, and I'll just use the variable C. Finally, the number one issue that students will screw up on with the lab is the change in temperature for the metal. The reason why I say this is they want to just use 13.4 degrees Celsius. But that's how much our room temperature water changed by. The metal started at 100 degrees Celsius. It was put in boiling water for several minutes. So this is the T initial for the metal. Get in that lab. They heat up metal in boiling water. They put it in a calorimeter. The water in the calorimeter heats up. What's the final temperature of the metal going to be? It's going to be one of these two numbers. Which one do we think? So again, we take hot metal, we put it in a calorimeter with water. The water temperature increases. What about the metal inside here? Should be the same temperature as its surroundings. Remember, I put a cold soda in here, it's going to be the same temperature as its surroundings after a while. If I put a hot coffee in here, it's going to be the same temperature as its surroundings after a while. So, to solve for delta T, it's final minus initial. 35.7 minus 100. Again, 35.7 minus 100. That will give me a negative change in temperature. 64.3. And now, ladies and gentlemen, we have algebra. Isolate your variable. Divide both sides by 75, divide by 64.3. Remember, that's a negative. The nice thing about this is you have two negatives. The two negatives will make it a positive. And now, since I'm at the end of my calculation and all I've been doing is multiplication, I'm going to use 2 sig digs in my final answer because this measurement here only had 2 sig digs. This is the type of calculation that we need you to do on your lab today. So that's why I wanted to go over it here first. But once you get done with this calculation, maybe you want to keep this sheet out as a reference, but then also have out the lab that you picked up on the way in, which is titled Heat Capacity of Iron Lab.